Hello, chemistry folks, and welcome to Solutions, where you'll find all the answers. Not really, I'm just kidding. So what is a solution? Well, it's a homogeneous mixture, which means it looks the same throughout itself, in which the physical properties depend upon the concentration and the strength of the interaction of the particles that are inside of the actual solution. So it depends on the solutes and the solvents. So a solute is the substance that's about to be dissolved in the solution, and a solvent is the medium at which everything is being dissolved in. Okay, so some examples of a solution would be like sugar water. So here's my container, right? Here's my container. I'm going to fill it full of water. The water is my solvent. Okay, and then I'm going to dump sugar in it. There's my big sugar molecules. The sugar is the solute. So the solute dissolves in the solvent, but the properties can still possibly be the same. You know, if you were to taste sugar yourself, and then if you were to pour sugar inside of water, you would still taste sugar in the water. Nothing about it is actually changed. It's just being dissolved in a substance. So any solution has two parts, a solute and a solvent. So there are three basic steps on how we create a solution. All right. This happens in a very specific way. So, okay, so I'm going to make my sugar water solution here again, and here's the steps. So I have water. I'm going to drop a clump of sugar in it. So my sugar, which is the solute, is going to start to expand. It's going to break up. And when it does that, when it expands, the water molecules, there's physically little water molecules, are going to come in between all of those parts. Basically, the sugar has overcome the intermolecular forces in between the water molecules. And so step 3 would now include there being some sort of interaction between the solute and the solvent. If there's going to be any type of interaction, like if they're going to break up into charge, conduct electricity, anything like that, now that's going to happen. So to reiterate, I have my water right here. I'm going to put something in it like sugar, and it's going to start to expand and come apart. And when that happens, step 2 would be the solvent, or the physical water molecules start to come in between there, overcoming the forces that hold sugar and sugar together. And then everything else is going to expand. So here's a better picture of me creating a solution here. Inside picture number 1, the solvent is what looks like the water, and the solute would be like a block of sugar that they just dropped in there. And so when you drop the block of sugar in, the solute starts to come apart, right? And after it comes apart, step 2, the solvent particles start to move apart and come in between each other and the other particles of the solute. And finally, step 3 would be where the actual molecules of the water, per se, the molecules of the solvent, kind of surround and get in between that solute and keep it apart from the rest of whatever else is in the container, like the rest of the sugar block. Okay, so not everything forms a solution. So why do some things form solutions and others do not? The very simple answer is this. If the solute, the sugar particles, are more attracted to the water than the actual sugar particle is attracted to another sugar particle, then it's going to come apart. So we dissolve most things in water. Essentially, if the solute, or the solid, in this case, which is coming apart or dissolving in water, likes water better than it does itself, then it's going to be more attracted to the water than it is to its actual self. This is intermolecular force interaction. The forces between the actual sugar molecule to a sugar molecule and a water molecule to a water molecule and a sugar molecule to a water molecule. I guess what I'm saying is that it's in between the particles itself. Now, also, in order for something to dissolve, it has to be like itself. Like it has to have forces that are like the forces inside of itself. And so we say like dissolves like. Now, water is really great at forming solutions, okay? It's not the only universal solvent, but it is pretty much on the top of our list. It likes forming solutions because water is polar. And that just means that here's your water molecule down here, and it has poles. It's got a positive end, and then it has a negative end. So much like, the Earth or the North and the South Pole or a battery that has poles, there's a positively charged section and a negatively charged section. And because of this, it becomes polar. We say it's polar. And it interacts and likes to interact with a lot of different things. A lot of things are more attracted to water than they are themselves. And so we say not only does like dissolve like, but polar dissolves polar things. And if water is polar and oil does not dissolve in water, then oil is nonpolar. And if you look at the molecule right here, here's your partially positive and negative, water molecule. And so the negative side is attracted to the positive side of another molecule of water. Okay, so water likes itself a lot. If I look at the oil, an oil here, which is essentially a fat, right? It's a lipid. There's no charge. This is a very linear molecule, and it's symmetrical, and so there's no positive or negative end to it. It's not operating kind of like a battery, almost like the water molecule is. So it's nonpolar. So in this case, we say the interactions between the water molecules themselves are stronger than the interactions between the water and the oil molecule. All right, so what's this about food coloring? So why does food coloring mix with water and not with oil? Well, is food coloring polar or nonpolar? The truth is that food coloring is actually polar. And because we know that because it dissolves inside of the water and not inside of the oil, like dissolves like, we don't even have to draw the food coloring molecule to understand that it has positive and negative, sides. So here's my polar bear, and he's drowning. And he asks the other bear, "Help, help, I'm dissolving in water." But the bear says, "But bears are insoluble." And he's really talking about polar bears. And our little polar bear here is obviously not polar, because if he was polar, he would be dissolving in water. Which is a bad name. It's a bad chemistry humor.